Hey guys, I wasn't expecting that many people, so welcome everybody to my talk as presented. Yeah, I'll be talking about integrating frame generation techniques into Cyberpunk 2077. And yeah, the agenda will be as follows. We'll do a little bit of the introduction of actually what the frame generation is. Like the overview of all the internals and stuff. Then we'll switch to the drawbacks and caveats that it carries on with it, because of course nothing comes without a cost. And then some issues and solutions that are strictly connected to the Cyberpunk 2077 integration itself. So they are not like frame generation oriented, they are Cyberpunk 2077 and our Red Engine 4, kind of like that kind of thing oriented. But before we start, I'd like to talk a little bit about myself, because that's my first rodeo from the industry. My name is Cezary. I'm rendering engineer at CD Projekt Red. I've graduated Warsaw University of Technology back in a time, CAD/CAM system design specialization. And even though it was like a couple of years ago already, it's still important because besides that I'm working here as a rendering engineer at CD Projekt Red, I'm also a university teacher doing some graphics lectures and programming as well. So that's that, but I've started my journey with rendering as a professional back in time at 11-bit Studios, working on Frostpunk 2, like really early stages of Frostpunk 2. And the guys are actually releasing like in 2 months or so. So yeah, keep an eye on that, because that might actually be something. I've joined CD Projekt Red back in 2021. So of course, already after the release, and my first kind of like major patch was the next gen patch when we shipped, all the like support for current gen consoles already, because they are not next gen anymore. Why we're doing the presentation? So that's the first thing, and then the second thing, why the integration actually happened. As for the presentation, I just wanted to share knowledge with you. The knowledge that we actually gathered throughout the process of integration, not one but two. Frame generation techniques into Cyberpunk 2077. And then, as I already said, to share some drawbacks and issues connected with that and how we actually overcame them. And then as for the integration itself, of course, it's a cool technology, so it's really nice to have it in your game. But then that's not the only reason, because as a CDPR, we actually have broad collaboration with all the vendors. So back in like mid-2022 or something like that, NVIDIA guys approached us and said that, hey, we just got this magic bit of technology that interpolates frames. Maybe you want to have it. And we were like, duh, of course we want to have it. We always wanted to be, like a cutting edge company with a cutting edge technology in our game. So here it is. So what the frame generation actually is a technique that creates artificial frames between two existing frames. It works by computing where each pixel in a scene is going to be moving in a given frame, and then using that information to generate filler frames, inserting them in between frames that graphics card renders in a traditional way. Of course, it's a little bit complicated. Then I'll show you some graphs that will walk through that a little bit. But of course, as I said, we'll be talking about two frame generation techniques that we do have in our game right now, even though the one isn't released yet. So of course, first one would be NVIDIA's DLSS 3 frame generation, and the second one would be AMD's FSR 3 frame generation. Of course, those graphs are kind of important, but let me just break it down a little bit. So how frame generation actually works, because that's not that obvious. We do have our like traditional render pipeline where we're getting all the color, depth buffer, motion vectors out of it. And then we're doing all the other stuff like resolution scaling, post FXs. We're drawing UI onto that, and then the frame generation kicks in, right? And of course, the frame generation actually isn't just a solid block that does just a single thing. It actually it's compound. It has lots of different things inside, bits and pieces that can talk to each other. So out of the frame generation, we need something that is called optical flow, and I'll talk about that, why it's really important in a second. And then, basically we take all of those four kind of things. So we get our color, we get our depth buffer, motion vectors, and the optical flow that is generated out of the kind of like frame generation itself. And we feed that into the interpolation algorithm, which is, of course, part of the frame generation, right? And then at the end of the day, we just present our frame. And why the optical flow is so important is that if we just take those three into account, so we do have our depth buffer, motion vectors, and a color, it might actually seem like, it should be enough because we got all the information that it's needed, right? I mean, we got a depth, so we got information about the geometry. We got motion vectors, so we got all the information about how the pixels are moving, and we got a color, so like. What else is needed? And then apparently, if we just take those three into account, the result is as follows. So as you can see on the right-hand side, the image looks pretty okay, but it still has some caveats, right? I mean, if you take a look here, so the shadows, right? They are a little bit off. And that's because all of those three that we do have depth buffer, motion vectors, and color. They are not actually carrying enough information for us to see what the actual kind of like color or intensity of a pixel is. So basically we were missing some of those, and the shadows are actually not the only thing that might suffer in here, because those also would be particles, reflections, and whatnot. Like all the things that are not rendered into the depth buffer or motion vectors, that they are not drawing anything like that. So we also need to take into account all of those, and that's why the optical flow is so important, because it actually kind of like compares two consecutive frames that the engine gives to the frame generation itself, and then the magic happens. So as you can see in here, we do have depth buffer, we do have our color. So that's even though they are off the slide right now, they are still there. We do have our motion vectors, and then in the middle right now we do have the optical flow. So you can see, like, all the arrows that are pointing in the optical flow, they are kind of like the same as from the motion vectors itself, because of course it analyzes the frame. It uses the motion vectors actually to compute the optical flow itself. So of course, all of those would be connected. But as you can see, in all of those places where we actually, have some details that shouldn't be interpolated like in a normal manner. We do have a little bit of a different thing for the optical flow. So that being said, let's focus on how the frame generation works under the hood, but because that was kind of like the arty part, right? But there's also the technology part and how it actually hooks into the game, because that's also not as trivial as it might be. So in the traditional pipeline, we'll just have our DirectX present function, and then it will just shoot to the OS, presenting the final frame to the player. But of course, the frame generation works by kind of like intercepting our calls to the API. So instead of just going directly from the DirectX present to the OS, there's interception going on, and the interception goes to the frame generation itself, to the the whole magic happens. And the worth mentioning thing in here is also that the frame generation actually also spawns another thread for our game, where it's called the frame pacing thread. There the whole magic happens. So of course the first thing would be the interpolation of the frames that we need to present. Of course, then there's a present, but we're upon the game calls a present method, the frame generation actually provides and presents the interpolated frame. right? So that's the first step. And then it kind of like saves the current frame for later usage. Of course, then we need to wait because we need to times all of those frames in a consecutive manner without any spikes and stuff. So we need to wait a little bit. And of course, it depends on the hardware and on the specs that you have. And then after a while, it presents the rendered frame, right? So that being said, the first drawback kind of thing that we can think about is the input latency, right? Because in a traditional pipeline, once again, we do have our update and present, and like, of course, there is some latency related to how we need to process our input, how we need to do the update, do the simulation, and schedule all the rendering. But it's still kind of like within the frame, right? But with the frame generation pipeline, as you can see in here, it's not that easy, because we're doing our update, and whenever we do our present in a game, the frame generation presents the interpolated frame, and then after a while, it presents the original frame. So as you can see, I mean, you can basically see in here that maybe I'll just do that. So instead of like just having a latency like this long, we're having latency this long, right? And of course, there's a way to overcome this, and it's called NVIDIA Reflex. The AMD has something similar, but it's not configurable, at least from what I know. So I'll just talk about Reflex. And in here, you got a like kind of like the second graph that shows what happened. The really important thing is to note that it only works properly, or it only does the magic, quote, when we're GPU bound, because if we're CPU bound, there's kind of like nothing to spare and nothing to shuffle around. But if we're GPU bound, so we can see like the input and the sim and update, those are kind of like the CPU parts, right? And then the render and present, we can kind of think about it as the GPU part. So if we're GPU bound, if our GPU is actually doing a lot of work, our CPU just stalls, right? So we do have our gap between the acquiring the input, doing the simulation, doing the update of all the entities in our game, and then actually scheduling a rendering, right? So what the NVIDIA Reflex does is it just tries to figure out how long the CPU is waiting for the GPU, and then it just moves around some bits and pieces of our frame in order to actually trying to fit the input and the simulation and the update of all the entities just before the render is being scheduled, right? So as you can see in here, we kind of like it's not technically a slip in the upper part. It's just kind of like a waiting, right? But it just it tries to slip our thread for a little bit in order to actually move the input and simulation closer to actual rendering. And of course, it doesn't overcome the issue like in 100%, but it's something. It's trying to be better, right? And of course, how to use it, how to integrate it, it's really simple. I mean, that's actually a part of our engine, but under the hood, it's just a kind of like a pass-through function with a little bit of validation. So basically, we just set a reflex marker saying that, okay, in here, we're just doing the simulation start, but in there, we're doing simulation end. In here, we're querying the input, and in here, we're not querying the input anymore. And then there's our present, and then there's our render start, and then the render end. So there's basically a couple of those enums that we can specify throughout our engine in order to, tell the reflex that, here are all the bits and pieces that you need to shuffle around in order to mitigate the higher input latency. Then the second thing is the UI composition, and it actually might be, I mean, it sounds trivial, but it might not be, because I saw some games not doing it properly and being or having some artifacts under the UI. Of course, I didn't have I didn't have that, but as you can see, I mean, UI sometimes is really complicated. Yeah, it's not just an alpha texture. I mean, of course, it's just an alpha texture with some things, right? But it's as you can see in here in Cyberpunk, we do have a little bit of a stretching, like ghosting effect that's there by the design, right? So if we not take into account a proper integration of UI composition, it might have some artifacts under the hood. And of course, the developers also thought about it, and we do have 3 approaches how to overcome that. As far as I know, the DLSS only supports the first one, but those 3 are for sure for the FSR. So first of all, we do have our headless texture, and I'll talk about all of them in a second. And then the second one is basically specifying a callback function, or like a present callback function that will draw the UI. And then the third one, the last one, is just like drawing UI to a separate texture. So yeah, the headless texture, we do have our rendering pipeline, right? Then we do have our like resolution scaling, post effects, and then from here, we're kind of like generating the headless texture. So before we go to drawing the UI as the last part of our game, we tag the additional texture that it's called headless texture that doesn't have HUD. It has all the things already. Yeah, we got a tone mapping, we got all the post effects, but it just doesn't have a UI. And then we're just fitting that into the frame generation, and yeah, boom, we're good to go, right? Because then the frame generation does the magic inside its composition function and basically compares the final texture with the UI that it got from the game with the headless textures that we also provided, and yeah, it just does the magic, right? And that's our implementation. That's the approach that we took in Cyberpunk 2077. So yeah. It just works, right? Then the second thing is, as I said, separates UI texture. So yeah, basically, of course, from our render, we just branch somewhere. We just like render the UI in like separate render paths that it's not connected into the post affixes, and then we just fit that into the frame generation. And those 2 techniques, they do have a little bit of caveat, because we're rendering the UI on our own only within the traditional pipeline. So whenever the frame generation actually presents the interpolated frame, it still uses the UI from the previous frame, right? So we do have, even though we kind of like overcome the input latency already, it still be there, right? So whenever we're running like 30 FPS, and then we do have 60 FPS after the frame generation, the UI still will be in 30 FPS, right? So those 2 approaches have this caveat, but like in general it works. In general, those are sufficient for you to use, unless you have like really crazy and fast, like animations on the UI that you really need to be top notch. So then there's a third thing. So the UI callback function that I mentioned, right? So whenever the frame generation calls a present, it actually calls our callback function. And then the engine can actually provide the code for actually rendering the whole UI over again, right? So with this approach, you'll have the same refresh rate of your UI as with your game, because as we already talked, the frame generation presents calls the present kind of like twice a frame, twice a normal frame kind of thing. And that would be this for the overview. I think those are all the bits and pieces that you should know. Of course, there's like tons of other stuff, but those are the most important that we actually found during the integration process. And then let's move on with the issues themselves that we actually encountered during the integration process that were kind of on the Cyberpunk side, not on the frame generation, right? And we got some and some more and a little bit more than that, because those are only those that I could actually find in our Jira with just searching for like DLSS and FSR3 and stuff, but there's been more, definitely more. But the first thing that we actually encountered that actually even postponed the release of DLSS 3 back in times. Yeah, we really wanted to release it like December 2020 or something like that, but eventually we released it like end of January 2023. And that's this storefronts overlay. The simple thing that, you know, that basically sounds really easy. I mean, it's just the overlay that, you know, like it draws over your UI, right, over your game, and like what's there to worry about? And yeah, of course, like showing you video, like when it doesn't work, it's kind of pointless. So yeah, I mean, here's how it works like right now, right? We do have our GOG overlay working with our Cyberpunk, and the issue was actually only present for the GOG. So the EGS and the NS team, they were okay. We only got an issue with the GOG overlay. And yeah, the first thing that we kind of like noticed, I mean, the game wasn't actually starting. I mean, we got, you know, like all the pipelines in place and stuff. The game was running perfectly fine when we were just, you know, running it on kind of like development machines. But whenever we installed it via the GOG, then yeah, it was instantly crashing, and we kind of like we were trying to actually wrap our heads around like what's going on. And the first thing that we've noticed is the hooking mechanism that the GOG is using versus the hooking mechanism that DLSS3 is using in order to hook into our game. So yeah, long story short, I mean, I'm not a hooking expert, so yeah, I'll just, you know, hand wave a little bit, but yeah, bear with me. Yeah, basically we do have like two approaches in order to hook somewhere. Yeah, we do have either proxy or hooking into the vtable. And those are the three things that, yeah, I think are kind of like important to understand, you know, the differences between those two. So the first one is a hooking time. So like what time of the like application lifetime we can actually hook into things. So of course, with a proxy, we need to hook upon the creation of our like new resources that we are using, and then with a vtable we can actually hook at any time because it's just kind of like swapping the pointers inside the vtable, right? Nothing that fancy. If it comes to implementation with a proxy, we need to implement the whole interface, the whole COM interface that comes with the with the interface or with the like factory, or I don't know, like DXGI factory or like device or swap chain that comes with it. And then with a vtable, yeah, since we just, you know, substituting some pointers inside the vtables, we can just substitute that and implement only those functions that are interested for us. And then the amount of hooks. So with a proxy, yeah, I'd say that, you know, like you can only have a single proxy. I mean, there's an asterisk because you can actually overcome that, but that's really, really difficult. I mean, maybe not really difficult, but it actually requires you to have like, a lot of careful implementation in order to, you know, like be threat safe, and in order to be sure that, you know, all the like previous like proxy creation is already done, and then it's just a little bit messy. But then with a vtables, since it's just you know, shuffling the function pointers around, you can actually store it in your class and then just call it whenever you want. So we can actually really easily chain those things. And so yeah, that would be the overview. But back to the topic. Yeah, we do have our overlay, right? And we do have our game with its swap chain, and without frame generation, yeah, we got our swap chain, we got our overlay. It was actually creating a proxy for our swap chain and then using that in order to, you know, draw the UI if needed, right? If user toggled it. But with the frame generation in place, it started to be a little bit more tricky because both of those were using proxies. And we kind of like didn't think about it at first, and it was really difficult for us to actually overcome that, right? So the ideal solution that we actually implemented was to change that into the vtables, right? So actually, I mean, the overlay, the GOG overlay actually right now comes with just the vtables, but if you integrating DLSS3 frame generation into your game, you can actually right now specify whether you want a proxy or a vtable hook, which is really cool feature, but it took us a long time. I mean, not us as like CDPR, but our colleagues back in NVIDIA, because it was kind of like three-end collaboration between GOG, NVIDIA, and us in order to actually get it working, right? So with this in place, we were kind of like good to go, because the game wasn't crashing and the overlay was kind of visible. Because then there's another problem, and that's the multiple swap chains. Because the overlay, the GOG's overlay, was actually only accounting for like a single swap chain. So we do have our game swap chain. We do have the swap chain from the frame generation, and the overlay was kind of like, okay, but where do I hook? Sometimes it was crashing, not that much as it was previously. Sometimes it was just flickering. Sometimes it wasn't visible at all because it hooked to a wrong swap chain and stuff. We needed an algorithm to actually think about it and like where to hook. And the obvious answer is we need to hook into the frame generation swap chain, because that already substitutes our swap chain in our game, right? We came up with the algorithm that actually kind of like recognize like which swap chain is which, and then it hooks into the frame generation swap chain, and boom, everything works. So that's really cool. The next issue that we had was the all sorts of hitches. Either we're talking about like going in and out of menu back to the game. You can see that basically it stutters from time to time. And then the second thing was not only when we were actually going in and out the menu, but also during a gameplay. We can see that we can actually experience some of those hitches in here as well. Of course, those were like the extremes, because right now we're talking, I mean, this video was recorded like 4K on, I think like it was like 4070 or something like that, so it wasn't that powerful card. I mean, in terms of, like rendering a Cyberpunk at 4K, and especially it was without any upscaling. So we were rendering 4K natively. There was lots of processing going on and stuff. So I mean, we needed a solution. We kind of like needed to take a deeper look at what's going on, because like besides that, everything's working already, right? We took an end-state capture. We sat down, we analyzed our frames, and we actually found bits and pieces that are responsible for that. Of course, those were like reallocations or allocations and stuff. So if we're talking about the menu itself, the DLSS is actually deallocating and allocating back again when we're actually switching between menu and a game. So that was that. We needed to kind of like overcome this either by waiting a little bit, but we eventually found out that I mean we can actually do we can actually like do the async compute kind of thing. I mean, we can actually schedule it on a different thread, then just wait a little bit, and then boom, all the things works again. In here it was a little bit more difficult, because like it was already in game, so we wasn't allocating the memory, we was reallocating them and shuffling things around. So this one was a little bit more tricky. I think we didn't overcome this like in 100%. Of course, right now it's way better. But of course, our recommendation is to utilize resolution scaling and stuff, because that actually helps your frame rate as well, not only hitches. But the like moving to a different threads, doing all the allocations asynchronously was a solution in here as well. And the last thing that I want to mention is actually the disocclusion artifacts that we've been having, and this one in particular is actually related to the FSR itself. So like those previous one were like strictly DLSS3. This one is FSR3. As you can see in here, whenever we're like moving around, Yeah, there's artifacts behind the car. That's not only it. We had lots of artifacts on the screen edges when the disocclusion happened and stuff. And of course, yeah, we took a pix capture, and then apparently it was a vignette. For some reason, the math behind the FSR wasn't able to figure out how the vignette is actually changing and how it should work in a proper way. So yeah, we kind of like was trying to once again wrap our head around like what would be the ideal solution. And yeah, we thought that okay, we cannot disable the vignette because that's like we really heavily rely on it. It's the first thing in our post process. So yeah, we kind of like cannot do anything about it, right? We cannot move it like later on, like after drawing the UI or stuff, right? So yeah, we kind of like came up with the idea of vignetteless texture, as I tend to call it. Oh, yeah. So that's our pipeline that we already had, right? We already have our headless texture kind of like generated out of the post affixes before we draw the UI. So we kind of like extended the behavior in order to actually have it, right? I'll just talk about it in a second. So that's the frame that we want to have. Yeah, that's the frame without frame generation, with the vignette and everything working properly. So there's no artifacts and anything. So yeah, as I said, from our post affixes, instead of just returning the headless texture, we also return the vignetteless texture. And of course, it's not that obvious how to achieve that, because as I said, the vignette is or was the first thing in our post process. So it was done before the tone mapping, before the film grain, before the chromatic aberration and whatnot we had in our engine, right? So we couldn't just tag it off and just like do all the stuff. So yeah, that's how the vignette-less texture or like the headless texture looked like before, right? And that's how it looks right now. So if we enable FSR3 frame generation, it actually changes, all of those textures. In here, I mean, of course, it's still like headless texture, but the color space is a little bit different, yeah, because like this one is already in the SDR, right, with all the post processing and tone mapping done, and this one is still having all the data inside, and that's why we could actually do the vignetteless textures. And of course, it looks silly, right? But it does the job, right? So if we take those two into account, so we do have our first one. We do have the vignetteless, or like not the vignetteless, but the texture with the vignette itself. But it's like kind of like the inverted vignette, right? Because we needed to kind of like invert our calculations in order to not have like negative results within the uint that we already have after the post processes, right? So yeah, it basically does the job done. It's working properly, and yeah, I think that would be the last thing for today. Before I wrap it up, I strongly recommend watching the video that we released like last year, March or April, something like that, when we were actually talking about DLSS3 and path tracing as well, because that was back in times like 1.1.6 or something like that, 1.62 or 3 back in April when we actually released the path tracing. We also released the video with Xiao, with Kuba Knapik and Giovanni, our specialist in terms of art, like the VP and the senior technical lighting artist, and Xiao being our like PR expert back in the time. So yeah, strongly recommend watching that, because that also goes a little bit in depth. I mean, of course, like from my part, it would be the same, but a little bit less. But the guys are actually really talking about, like path tracing and how we incorporated that as well. And yeah, before I thank you guys, I would like to thank you, for all the collaboration that we actually did for the integration itself. So of course, my team back in CD Projekt Red, the guys from the GOG that helped us overcome the GOG issues, and the AMD and NVIDIA for our beautiful collaboration, and especially Adam Sawicki from AMD and John Kennedy from the NVIDIA, because those were those two people from those two companies that actually spent hours with us trying to integrate, so everybody can actually have the frame generation and play our game with enormous frame rates. Thank you guys. And maybe before we jump into questions, if there are some, because I've been talking about the FSR 3 frame generation, that it's not public yet, but I'm actually able to say that it's in the game. It's already working there. So maybe sometime in the future. Who knows?
No questions for now. Maybe some more questions will arise.
I think this one,
there's one.
Hey, so the way I understood it, all those APIs that you use, those black boxes take some textures as an input, right? So you can just give the full color or splitted color and UI, right?
I mean, you always have to do the color, and you can split the UI with the approach of like being a UI as a separate thing or doing a UI as a callback, right? But the first approach and the approach that we did in Cyberpunk is that we're feeding two of those textures. The first one is having a full color with the UI, and then the second one is having a full color without the UI. And then, the magic happens inside the frame generation.
Yeah, I'm just not fully sure how this inverted vignette fits into it. Like, are you using this inverted vignette on one of those textures?
No, that's a separate thing. So let me get back to that. Maybe here. We do have our headless texture, right? So that's the standard approach. We do have the UI texture, right? So that's maybe I'll just do that. Yeah. So we do have our UI texture, so that the color with the UI that fits into the frame generation, and then we do have our headless texture, right? And then the vignette is actually just the thing to overcome, like, because whenever we had a vignette in our headless texture, it was actually causing all of those artifacts, like the occlusion artifacts, because of the maths that's behind it. So we needed to take the vignette out of the equation, right? But it wasn't so easy just to take it out and then apply it later, because in our post affixes we are actually doing all the color grading, all the post affixes, right? So so the approach that we did is like, we're doing the all the post affixes in our texture, in our resource, and then we actually subtract the color out of it. And then that's how the vignette-less texture comes in life. So it's not technically vignette-less because it actually carries all the information about the vignette and all the post processes that we done, in order for the headless texture to be just a pure color without the post processes.
Yeah, I guess just my question is, how the composition works, because you're probably talking more from the position of FSR, right? But I'm always working more with NVIDIA, and the NVIDIA APIs are usually black boxes, right? You just have the API, just one function call with a descriptor and texture handles, right? So did you actually went into the FSR code to actually composite yourself, or does it happen automatically?
It happens automatically.
Oh, okay.
Yeah, I mean, maybe not automatically. We needed to, kind of modify two shaders. So the first one was actually post affixes when we output the texture, and then the second one was the UR composition on our side. Yeah, so when we composing our UI, we actually taking the vignette-less texture on our own, because that actually happens, after that. Yeah, and then the FSR is actually doing the job, and that's only FSR feature. So for the DLSS, we're going with the normal approach.
Oh, okay, that cleans things up. Thank you.
Yeah, sure.
First, a great talk, a lot of useful information. I have got a question. In terms of API calls, why the whole architecture needs to be intercepted around the present call? So from my perspective, it seems like the whole issue with GOG was related. It was like intercepting twice, and like if it was an external tool, then okay. But you're working with your game. Why it's not just calling some different function within NVIDIA and AMD APIs, but intercepting the present call?
Because I mean, like for the GOG, it's kind of like obvious, right? Because that's an external tool, as you said, yeah, and it needs to do the interception, kind of like without us knowing about it. But in terms of DLSS and FSR, it's kind of the same. Like even though it's integrated into the engine, you know, the NVIDIA and AMD engineers, they really wanted to have the integration process as smooth as possible, right? So instead of just, you know, like us doing lots of works, that was just the easiest part kind of thing, the easiest way to achieve the hooking and, you know, like intercepting it.
Okay, thank you.
Yeah.
Okay, any more questions? We've got one more.
Firstly, great talk, Cezary.
Thanks a lot.
I'm really happy with how it turned out, and I saw the hard work you put into it, so I'm very happy it went so well.
Thank you so much.
But I wanted to ask a bit of a more philosophical question, I guess.
Okay.
Where do you see this technology going? Do you see it embracing the hundreds or perhaps even break the 4-digit mark of FPS, or do you think it'd rather go into the direction of handling lower FPS scores better, so being used on things like the Steam Deck or Xbox Series S to get those games to drive in 60?
Yeah, I think the latter one, because right now we're a little bit off if it comes to the low FPSs. For the DLSS, it's recommended for your game to run actually in at least 30 FPS in order to, you know, like frame pacing algorithm and stuff work properly. But for the AMD, it's 60. So if you're running less than that, I mean, of course it will work, but you may expect some frame pacing glitches that, you know, like frames are actually jumping from one place to another, and you're seeing the latter one before the previous one and something like that. So I think, yeah, we should actually focus on fixing those low FPSs and trying to overcome that before we jump into high FPSs. That's for sure.
Yeah, thank you very much, and
Thanks
again, thanks for the talk.
Thank you.
Is it going to be a question? Yes.
Hello.
Okay.
So I was just wondering, when you spoke about the UI callback, because you are rendering your game in 30 FPS and then it's being interpolated to up to 60.
Yeah.
When you are calling back on the UI, is the UI individually being rendered at 60 FPS or 30 itself and being interpolated?
Just a second. Let me just get back to the slide. Yeah. Here. Yeah, we do have those three approaches, right? And with the first one and the second one, we're actually rendering the UI as in a traditional way, right? So then whenever the frame generation actually renders a new frame, it actually just uses the UI from the previous frame. So it's not it doesn't interpolate, doesn't do nothing, it just uses it, just kind of like copy paste it into the like frame, right? The new frame. And then if we, first and third one, that was. And then if you really want your UI to be actually running, you know, like full speed, you need to do that with using the function callback. So like present callback to kind of think as in here, right? Yeah, we do have the arrow is actually like two-sided, right? So whenever the frame generation calls a present, it first calls the UI callback, so the engine can actually render the whole thing, the whole UI once again, and then it gets back to the frame generation. It composes it and presents, right? And it happens for those two presents that are inside. So then you're actually rendering your UI in a full speed.
Okay, thank you.
Sure.
Okay, any more questions?
Yeah, I think we're good then.
Okay, we're done. Okay, so let's thanks once again Cezary with the round of applause.
Thanks a lot, guys.